This is like one of the best introductory physics problems for the first semester because it involves so many different concepts. And let me describe the problem, and then I'm going to model the problem in Python, and then we're going to solve the problem. It's going to be great. So the idea is to have two objects, a ball or disk or some mass, some point mass, and this is in either on a frictionless surface or in space, whatever makes you happy, that's where it is. And so it's moving with some velocity VA1 towards this dumbbell, so two masses connected by an infinitely low mass rod, and each of these has a mass of m/2. So the mass of this and the mass of that whole thing is the same. It collides at a glancing angle, and so then this is my after. I always use that for, some time later. Mass A, the first one, is deflected off with some new velocity at some angle, but it's a vector. And then this mass is deflected down, and it rotates. And so what we want to do is to find, if I know the final velocity of this, what's the final velocity and angular velocity of that? It's going to be great. But like I said, I actually already made this animation. I made this model. In my model, what I did was to have a spring force between these to represent the collision. And then this is a mass connected by a spring. So that's how these two rotate. So it's just forces. It's just spring forces. And then we can compare the answers at the end. So let's look at the animation. So here, and I had another program based on this, but I'm not going to go over all the code. Basically, I just make two masses, three masses, and then I give them initial velocities. I also plot the center of mass of those two bars. That'll be important. And then I print out some stuff. Let me just run it because we can talk about the code. I don't really want to go over the code. It's really a physics problem. So here's my ball. It's a little bit big. So you can see that dumbbell is both deflected at an angle and rotates. Now, it's not a rigid object because it's connected by a spring, but I put a very large spring constant there so it doesn't shake too much, and that should be fine. You could always increase the value of that, but I printed out the final velocities and everything so we can check. But let's go back to the paper and do this as a physics problem. Okay, so let's start off with, I want to find this velocity right here. And how do I do that? Well, it looks like a collision, but it's more complicated because this rotates. However, if I treat this as a point particle, where it has a location at the center mass, I can find the velocity of the center mass just by treating it as a point. And you may think, that's not fair, you can't do that, but I can. If I declare my system, let's call this A, and let's call this whole thing B. So this is A, and this whole thing is B. My system is A plus B, those two objects. In that case, what's the net force on my system? It's zero. There's no external force on my system. That means that delta P, delta T of the system is zero. I just wrote zero twice. Or I can write initial momentum is final momentum. I can do that. Well, let's write it out. If my initial momentum is just the momentum of these two things added together, but this is at rest. So I can say this is mass. They both have a mass, m, times VA1, the initial velocity vector, which I know is moving in the x direction, plus the mass of this times its velocity, which is 0. And that's going to be equal to the final momentum. I'm just going to write that as mVA2 plus mVB2. Remember they have the same mass. And because they have the same mass, I want to solve for VB2. So I can divide both sides by the mass in this case, and I can solve for VB2. VB2 is equal to VA1 minus VA2. That's it. Now, if you wanted to do this in terms of the components, if let's say you had the magnitude and the angle, I could write VA2 like this. VA2, the vector, is equal to VA2, the magnitude, times the cosine of theta A, and then VA2 sine theta A. And I go around a room, 0. There. So then I could, if I want to just find the x component of VB2, it would be the x component of this, which is, I know, VA1. So let's just write that out. VB2x is going to be VA1, the magnitude of the velocity is only in the x direction, minus VA2 cosine theta A. And then you could do the same thing. Let's write it out. VB2y is going to be 0, right, because it has a 0y velocity. 0 minus VA2 sine theta A. And that makes sense, right, because this one's going to have a negative y component. And so this is going to be a negative number right there. And we're going to calculate that, don't worry. But I'm really just going to calculate it twice. I'm going to actually measure the velocity at the end, and then I'm going to calculate it this way too, and see if I get the same thing. And that one's pretty easy. And the hard thing about this is that you think it can't be this easy. You think, well, I have to compensate for the rotation of that rod. And if you're dealing with the center mass, it doesn't matter. Okay? It just doesn't matter. Now let's find the rotation of the rod. So let's, again, take the system of A plus B. A plus B. And now I'm going to use the angular momentum principle. This says that the torque about some point O, the net torque, is equal to the change in angular momentum with respect to time. And remember, angular momentum about some point O for a point mass is R cross P. Angular momentum about some point O for, we don't need that. We only have, no, we will. I'm going to say this is I omega, where I is the sum over I, mi, ri squared. So the moment of inertia, you just take all the masses multiplied by the distance to the point of rotation squared and add it all up. And then the angular velocity right there. Now, let's just think for a second. Let's look at the initial angular momentum. Oh, and if my system is this, then the torque on the system about point O is 0. And this means initial angular momentum equals final angular momentum. So that's what we're going to use. Now, angular momentum is a vector, but since we're in a flat plane, we actually, all our angular momentums will be in, let's say, the z direction or negative z direction. So let's look at that initial angular momentum. Here's mass A, and here's its velocity, VA1. So it has momentum. And then here's my rod. I'm going to pick the center of the rod to be the point O. You can pick wherever you want, but it's going to be way easier with this. So this comes in like that. It's actually not the same as R. I shifted it up a little bit. So let's call this R. Well, let's first look at this. If I'm at this point right here, RA1. So if that's a vector, and I do the cross product, this has no initial angular momentum. I hope we can see that because it's not moving. LI is RA1 cross MVA1, R cross P. Now the cross product, if you remember, the cross product depends, the direction of the resultant is perpendicular to both R and VA1. So let's just draw that right here. Here's R, and then here's VA1. And so there's two vectors that are perpendicular to both of those. There's this one, and there's this one. This one's a vector coming out of the paper. This is going into the paper. And we used our right-hand rule. See, that's my right hand. And if you let your fingers cross through R and then V or P, then you get the direction. So that would be this one. And so if I have this is X, this is Y, then that would be in the negative Z direction. But it's important that it's in the Z direction. And then when this thing rotates, it's going to have an angular velocity that way too, so it's going to be in the negative Z. Everything's in the negative Z direction, I think. No. Well, that's fine. We'll write this. We'll deal with this in the Z direction then. So we don't have to worry about writing these as vectors. Now, the other thing is, if I have this thing moving along here, the angle between these two is theta, but once I get over here, the distance decreases, and the theta goes to 90 degrees. And so I can actually use this location right here, where the mass is, to find the angular momentum. So let's say Li is going to be, it's going to be negative in the z direction. These are all z directions. I'm not going to put the z component. Negative m va1 RA1, where that's this RA1 is this distance right here, which is a little bit bigger. I actually had this RA1 as 0.3, and R, the distance from here to there, is 0.2. So it's a little bit bigger. If I didn't do that, then this wouldn't get deflected up, so I had to have it at an angle. But now I have the initial angular momentum. What about the final angular momentum? So this is a lot more, well, it's a bit more complicated. Let me draw this on a separate sheet of paper. I want to draw the instant after the impact. Instant after. So here's my mass, my bar. That's my point O. And now this actually is moving down, right? It's moving down because it got deflected. This is VB2. This is also going to be rotating this way, omega. And then my mass A is up here, like that. We'll call that VA2. And that's my point O. So I actually have 3 angular momentums. LF final is going to be LA. These are all vectors in the z direction, but I'm going to call them just constants. LA2, the angular momentum of this, right? It has angular momentum, plus LB2T plus LB2R. So this is the translational angular momentum. This is R cross P, and this is I omega. It could have both of those. So I have 3 terms for the angular momentum afterwards, and I want to find that omega. So this one right here is the first one to deal with, right? Because if that's my velocity, and that's my direction of the momentum too, then it passes right through the point, because it is the point. So R is going to be 0, so this whole term is 0. And that's why it's really nice to pick that point right there. This term is not 0 though, okay? So remember, we have some angle theta too. I'm actually going to include that in here. Because now if I want to calculate this, I know this is straight up as RA1. That's the value of that. And I can put it up here, RA1. So this angle is going to be pi over 2 minus theta over 2. And that's the angle between R and the velocity. So I can get LA2 is going to be RA1, which I know, times M times VA2 times the sine, or actually it's going to be cosine of theta 2. And it's because I use the sine for the cross product, but if I have the complement of the angle, I'm going to use cosine instead. Is that okay? You could also think of it as this. I'm going to take this component of the velocity, which is perpendicular to that, and then, so it's VA2 cosine theta 2 is a perpendicular component. But that gives me my angular velocity, angular momentum, and it will be in the negative z direction, so let's put a negative sign right there. So now I just need this one, and that's just going to be I omega. So what's I? In this case, I is going to be m over 2 r squared plus m over 2 r squared, right? That's 1/2. That's the mass of each one of these pieces times its distance from the point of rotation. So it's just going to be m r squared. So now I can put it all together. My initial angular momentum was negative m va1 RA1, which is 0.3, and that's going to be equal to the final negative RA2 MVA2, which I know that velocity, cosine theta 2. I could do R cross P. I can do that, right? If I don't want to find that angle theta, you could replace this with the magnitude, negative the magnitude of the vector RA2 cross mva2 vector. But this is the way you do it on paper. So that's that one. And then I have, is this going to be a positive or negative angular velocity? It should be negative also. Negative mr squared omega. And then I want to find omega. So let's add this to both sides. So I get, let's add this to both sides. So I get mr squared omega is so that goes over here, that goes mva1 ra1 minus ra2 mva2 cosine theta 2, and then just divide by mr squared. So omega is going to be, the mass cancels. It's going to be va1 ra1 over r squared, that's right, minus ra2 va2 cosine theta 2 over r squared. Now, a quick note. You may say, hey, couldn't I use energy? Couldn't I say the work is 0, and that's the change in kinetic energy of A plus the change in kinetic energy of B plus the change in rotational kinetic energy? That's a great idea. And it, in theory, should work if you have actual elastic collisions between these things, which you don't always have. We don't know that it's actually an elastic collision. It is an elastic collision because I made it that way. But and the energy stored in the spring is very small because it doesn't oscillate that much. So that would almost work. But this is the better way. Okay, so let's go and check the velocity, right? So I want to measure the velocity of my recoiled rod and then calculate the velocity of my recoiled rod. And I actually think I already did this. So let's go back over here. So what I did, the first thing I did was, let me make this bigger so you can see, is I print the mass, just so you know what that mass is. The initial velocity is, I originally put it in terms of momentum, so I divide by the mass. And then R. I should also print RA1 is going to be equal to, what would that be? B1. It's b1.pos.x. b1.pos.x. That's the, I'm sorry, y. That's the y value. That's how far from the thing it is. And then I actually calculate right here v1 because I want to use it later, just as a value. And then down here you see I calculate the forces. This is the important thing right here. If there is a collision between the two objects, if they're overlapping, then there is a force pushing them apart. This L is a poor choice and not a future-looking choice. That's the actual vector from one mass to the other. I use that to calculate the force. It's not the angular momentum. And then I calculate the kinetic energy, stuff like that. Afterwards, here I have V2. This is the measured V2, right? That's just the momentum of ball 1. This is VA2, which I'm calling B. After the collision, just because I've been changing that value. Now I calculate the theta between those two, right? I'm choosing magnitude divided by the x component, or the x component divided by the magnitude, take the inverse cosine. I print that angle theta, V2. Why did I do that? That's the magnitude. I don't really know why I did that. And then here's V2. Well, I did it again. Weird. So right here, this is the, remember we calculated the velocity, I'm calling it V3, of the recoil object. I just said it was the V1 minus V2, the mass is canceled. And then I print that right there. So I want to compare this value to the actual value, which is, I'm calling V2, surprisingly. That's velocity VA2, theta. Oh, this is V2. No. That's the velocity. Oh, here's when I actually measure the velocity. So I have two objects rotating for that bar. I need to find the momentum of the center of mass is just the average momentum. I can sum up the momentums. So it's momentum A plus momentum B, and then to find the velocity of the relative center of mass, I divide by the total mass, which is m. So this P3 is actually V3. V3, let's say, measured. So that's that. Let's print that. So print V3. I printed it twice. I don't know why. Let's print. I printed up here, and let's put this V3M. Okay, let's just run this and see if these things work. I kind of messed up my code here, but messing up's part of being just, doing stuff. So we already saw that. Okay, so V3, so I get the same thing. This is what I'm looking at right there. I get the same thing. Okay, that W is wrong. I do print out the angular velocity. So how do I calculate that angular velocity? I'm measuring the angular velocity right down here. So what I did was to take the velocity of this mass relative to the center mass and divide by the radius. So that's how that calculation is. But I want to do one last thing, and that's to calculate the angular velocity based on our calculations over here. So let's go and add that, and then we'll be done. So I'm going to call that omega 2 calculated. And I'm just looking at my equations over here. It's VA1, which I have as a number, V1, V1 times RA1, which I have as a number, as a magnitude. Did I? RA1. I'm so messy. Print RA1. Let's just call that RA1. RA1 equals b1.pos.y. That's fine. RA1 divided by R squared. That's all just scalar values. And then minus RA2, which is RA1, times VA2, which do I have that? VA2 right there. Let's call that a thing. VA2 equals b1.p magnitude. Yeah. Mag b1.p divided by m. And then I do have theta right there, so I can use that theta. VA2 times cosine theta, I just call it theta, divided by r squared. Okay, and let's print that. Let's see if it's the same. W2C calculated. W2C. This may not work, but I think it's going to work. But it may not. Here's the collision. Boink. And I calculated 22-degree deflection. That seems reasonable. And I cannot subtract a scalar and a vector. That's my fault. So what did I do wrong? Right here, VA2 is the velocity at the end. That must be a vector. V1 is a vector. So let's put this as a mag. And then RA1 is the scalar. Scalar, RA1, VA2. What's VA2? Do I even have VA2? There it is. Okay. So I think I'm okay. I think that was it. Okay, so I'm off a little bit here. I'm off by a factor of 10. I feel like this is the right one. I think I'm just making a mistake with my calculations. I think it's all legit, and I'm not going to double check it because I have such a messy code. I'll give you the code, and you can fix it. I'm pretty sure my calculation over here is correct on the paper, so there you go. That wasn't as much fun as I thought it'd be, but sometimes you got to do stuff that doesn't work out perfectly, and that's okay with me. It's a learning process, right? Okay, that's it. Code down below. The end.